Assalamualaikum and greetings to Dr. Dayang and also Dr. Shakina. I am Muhammad Nurdina Beroslan. My matrix number is 207840 and I am one of the group members of Group 4. Today we're going to present to you about our project. Our group name is 4 Frost Neighborhood. 4 Frost consists of 4 members. There is Wang Zonghan as our group leaders, Siti Aisyah binti Muhammad Isham, Kishan Raj anak lagi Siva Kumar, and also me. In this project, we are requested to produce 1.2 million tons of ammonia using coal as our feedstock, and we also required to using Haldor topsoe technology. So what is Haldor topsoe technology? Haldor topsoe technology is located in Denmark for their global headquarters. Their mission is want to be the global leader within carbon emission reduction technologies for the chemical and refining industries. So this is the type of coal that we are using, that is enol 6, and this is the coal composition of it. So this is our main units for the production from the wet coal to ammonia, that consists of coal dryer, gasifier, air separation unit, COS hydrolysis, sour shift, dual stage selector unit, pressure swing adsorption, ammonia converter, and also refrigeration. So next part will be presented by my colleague. Thank you.
Hi, here is Wong, going to explain more on the part of process selection route. So the main journal that we are referring to is this. In this journal, we use the case 4 as our reference because it is closer to our project, where we aim to produce the ammonia from the coal. Okay, since you can see the case 4 is not only produce the ammonia, but at the same time it produce the syngas. So we try to do some amendment where we eliminate the part of producing the syngas, and we do also insert the Haldor topsoe technology in the block flow diagram. Okay, so me and Aisha will explain more on how we do it. Okay, so we start from the first unit that we use is coal dryer. Okay, because the gasifier that we use is a dry gas gasifier, where the lower the moisture of the coal, the higher the efficiency of gasifier. So we need to dry the coal into 6% moisture. Okay, this one also referred to the journal. And then after we dry the coal, then the dry coal will enter the gasifier to undergo a series of the reaction where we call it as the gasification. Okay, under the gasification, we have the pyrolysis, we have oxidation, we also have the reduction reaction. Okay, for the gasification to occur, we need to have the stream of the coal for sure, and then we need to have the stream of the steam and also the O2. Okay, so some of the assumptions that we have made and the extra information that we have gained in the journal is first is the O2 to coal ratio, and then carbon conversion, and also some of the product ratio. Okay, because since the input of the gasifier and also the condition of gasifier is exactly the same as the journal, so we assume that the ratio of the product will be the same as the journal. Okay, so through this all the information we can calculate the material balance. Because you can see we have the stream 2, this one is for the O2, right? So for sure we have a unit called air separation unit. So for this air separation unit we will insert the air into it, and then it will separate the O2 and nitrogen and oxygen. For the oxygen, it will enter the gasifier, while for the nitrogen, it will use in the PSA unit and also the mixer too. Okay, so we have another separator here to separate the nitrogen into the required amount for the mixer 2 and also the PSA unit. Then for this ASU, what assumption that we have made is we assume that in the air only have O2 and N2. Okay, we ignore the argon to ease the calculation. And then we move to another part. We go back to the gasifier. After the gasifier, it will enter a raw gas cooler because the condition inside the gasifier is the temperature is quite high. So we need to reduce it from 1,499 into 260 to for the further reaction. Okay, then we go to the COS hydrolysis. For this COS hydrolysis, it is used to convert the COS into the CO2 and H2S. Okay, the reason why we want to convert the COS into CO2 and H2S is because first, our sour shift has used a catalyst called SSK10. Okay, this is the Haldor topsoe catalyst. For this catalyst, it will be poisoned by the COS. So that's the reason why before it enters the sour shift, we need to convert the COS into H2S to avoid the poison occur. So in this COS hydrolysis, the catalyst that we use is CKA3. Okay, This one is also the catalyst from the Haldor topsoe. Okay, so from this, we assume that all the COS will be converted into CO2 and H2S by reacting with the water. Then we go to another unit, which is sour shift. For the sour shift, because the reason why we use the coal is to get the H2, okay? So the sour shift is to increase the amount of the H2 by undergo a reaction where it converts the CO into the CO2 and H2. Okay, so it will react with the steam that we insert into the sour shift. For this part, we have made some assumption where is the fractional conversion of CO, and also we have the H2O to CO ratio, where this all the information we can get from the journal. Okay, then after the reaction of this sour shift, we can get the higher amount of the H2, and this gas, this stream will enter to the cooler, and inside this cooler, it will be lower down the temperature from 288 into 25 for the further reaction. Okay, later Aisha will explain more on the rest of the part.
My name is Sita Aisyah binti Muhammad Isham. I will continue explain about the BFD. So the mixture from the cooler is moving into the mercury removal with flow rate of 816,487.72 kg per hour. Basically, the function of this unit is to remove 0.15 ppm mercury before entering acid gas removal process. The outlet flow rate remains the same as the inlet. For acid gas removal process, Haldor topsoe use dual-stage Salazar process to remove hydrogen sulfide and carbon dioxide. In the first stage of Salazar process, stream 19 enters the H2S absorber and 129,668.18 kg per hour DPEG enters the H2S absorber. DPEG will absorb H2S out of the stream and will enter the stripper, and the remaining components will enter the CO2 absorber. Extra information for this unit is solubility of H2S is 8.82 and solubility of CO2 is 0.485. In H2S stripper is where H2S is separated from DPEG. 5,130.04 kg per hour H2S is removed and 100% recovery of DPEG will go back to the absorber to continue the process. In the second stage of Salazar process is where CO2 is removed. Stream 33 refers to the remaining components from H2S absorber will enter CO2 absorber. Stream 36 refers to DPEG enters the CO2 absorber, and DPEG will absorb CO2 out of the stream. Extra information is CO2 captured efficiency is 95%, and stream 37 refers to the remaining components that will enter the pressure swing absorption unit. In CO2 stripper is where CO2 is separated from DPEG. 420,692 kg per hour CO2 is removed and 100% recovery of DPEG will go back to the CO2 absorber to continue the process. In the inlet stream from CO2 absorber will enter pressure swing absorption unit to purify the stream before entering ammonia converter. PSA also helps to separate hydrogen and nitrogen from other compounds. Stream 4 is where purged nitrogen from ASU is entering the PSA. The hydrogen recovery efficiency is 94% and PSA produces 98.8 volume percent of hydrogen. And then the purified hydrogen stream from PSA will go to the mixer to combine with nitrogen from ASU to maintain a 31 molar ratio of hydrogen to nitrogen entering the ammonia converter. The fraction of hydrogen is 0.75 kmol per kmol and the fraction of nitrogen is 0.25 kmol per kmol. The combined stream is then entering the compressor 1 to increase the pressure from 3.24 megapascal to 13.62 megapascal. The outlet flow rate remains the same as the inlet. Stream 31 enters the ammonia converter to convert hydrogen and nitrogen into ammonia. The conversion rate is 98.21%. The outlet flow rate is 9,254.91 kmol per hour. The ammonia product is compressed to 7,600 mmHg before entering the refrigeration. Stream 33 enters the refrigeration where ammonia is refrigerated to negative 35 degrees Celsius. Hydrogen and nitrogen remain in gas phase. Stream 35 is the desired product 151,515.15 kg per hour liquid ammonia. The dew point temperature obtained is 23.87 degrees Celsius at the temperature of 7,600 mmHg.
The next part is costing and cash flow analysis. We took our supply of feedstock, which is coal from US Coal Global Group in South Africa. Since we are using 1.7 million ton coal per year as our feed, the average total cost for the raw material is 0.4 billion ringgit. Meanwhile, the average market price of ammonia is 110 ringgit and 75 cents per ton. Following this selling market price, our ammonia produced at a capacity of 1.2 million ton per year gives us an annual sale revenue of 1.2 billion ringgit. The plant is built near water source area, so raw material price for water is excluded. This figure shows the cumulative cash flow for the first 20 years, which follows an upward curve instead of linear. This is because in our costing analysis, we use the projected cost of the coal and ammonia market price over the next 20 years based on the world demand. Therefore, the operating cost and the selling market price of ammonia would increase every year and contributing to the curve pattern. At the start of the first year, we already made a profit of around 0.8 billion ringgit and continue to make profit afterwards. With a production of 1.2 million ton ammonia per year, we could generate a sale revenue of 1.2 billion at the first year. Therefore, the production of ammonia from coal using Haldor topsoe technology can produce a great amount of profits from this project according to our cash flow analysis. For recommendation of future work, we plan to add some units after H2S removal unit. This is because we can convert H2S to sulfuric acid that has wide consumption on it has to manufacture detergent, pesticide and synthetic fibers. In conclusion, Phosphorus company will produce 1.2 million ton of ammonia per year with 100% purity by feeding 1.7 million ton per year of wet coal. That's all from Group Phosphorus, and thank you for watching this video.